Alright, so here we take it up a notch or two. We've got this limit of this crazy thing here, and we're going to go through the same steps as before. First step is we're going to try to figure out what does that smell like. Second step is we'll try to verify. And it'll go, the verification step will be this one right here. We verify the limit of the quotient of the one that we have, that's that one, and the one that we think it smells like, we'll cook that one up. And then we'll verify the second step, make sure we're allowed to slap a sums on both sides. To do that, you need to make sure that either one or the other one is positive. Here I can already tell you that these ones are positive for large n's. Because look at that, you got positive, 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 positive. That one I can already tell it's going to be fine. And then we can declare this one the same as the one we think it smells like. And hopefully that we pick out one that smells like that's easy to compute, so that we can see if it converges. So that's easy for us to see if it converges or diverges. Anyways, you know what they say, talk is cheap. Let's do it. So what do you think it smells like? So this time I'm going to think in red. I'm feeling a little red today. So for this one, I think that the 3 plus the ln of n plus the 3 to the n, I think in this case the 3 doesn't matter that much, and I think the ln is so small compared to 3 to the n, so I think that one doesn't matter either. So I'm going to go with a little thicker thinking. On the bottom, is that better? Yeah. I think that the square root of n is not that important, pi is not that important, especially when you compare them to 5 to the n. Hold on. Especially when you compare them to 5 to the n. So if you compare them to 5 to the n, the 5 to the n is so much more powerful than, say, the square root of n. So I think that really this series smells a lot like 3 to the n over 5 to the n. That's what I think. Okay, now I need to verify it. To verify it, I look at this quotient. I'm going to look at the quotient in white. So I have, no, I'm going to look at the quotient in yellow. Why? Because I can. 3 plus ln of n plus 3 to the n all over square root of n plus pi plus 5 to the n. All that, I think it smells like 3 to the n over 5 to the n. So I'm going to check this limit. If I could check this limit, I'll be in business here. I'm going to do a little bit of simplifying here. So I'll flip it, so it'll be 5n times 3 plus ln of n plus 3 to the n all over 3 to the n times square root of n plus pi plus 5 to the n. Okay, that will be equal to, well, I still have limits on all of this. That would be equal to, let me think, 3 times 5 to the n plus 5 to the n ln of n plus 5 to the n. Wait, can I just say 15 to the n? Can we do that? Whoa. I'm going to say 15 to the n. Because 5 to the n and 3 to the n gives me 15 to the n. All that over 3 to the n times the square root of n plus 3 to the n times pi. Right? Plus 15 to the n. And this looks like a mess, but don't worry, I got your back. You look for the biggest guy here, biggest dominating term here. It looks like 15 to the n is dominating, and you divide everything by it. So if I divide everything by, I'm going to go with white, divide this by 15 to the n, divide this by 15 to the n, divide that by 15 to the n, divide this by 15 to the n, 15 to the n, divide this by 15 to the n. I think that turns into something like this. Let's go back to yellow. I think that turns into something like this. 3 over 3 to the n, because on the 5 to the n and 15 to the n, some of that stuff cancels, plus ln of n over 3 to the n, plus 1 all over square root of n over 5 to the n plus pi over 5 to the n plus 1. Alright, and now of course we were always taking the limit as n goes towards infinity. This will go to 0, this will go to 0. You might have to think about it a little bit, maybe do a little L'Hopital on it. I'll let you take care of that. This goes to 0. That goes to 0. I'll let you take care of this too. Maybe do a little L'Hopital. That goes to 0 just by plugging it in. In the end, you get that this is equal to 1. So this is equal to 1. That verifies this one. I had already talked about why one of them is positive. In fact, in this case, both of them are positive. The one I'm smelling out and the one that we originally had, both positive. So this is even easier. And that does it. That means that I can declare this one, the one I have, I can declare similar to the one I think I proved that it smells like, which would be this one. So here, this is the punchline right here. Once you've verified that you smell that out and you check the conditions, then you can say this is the same as that. Not the same, but they're similar, meaning that they both converge or both diverge. And of course, this is a geometric series. This n goes from, I can go from 0 to infinity. This of course becomes 3 over 5 to the infinity plus 1 minus 3 over 5 all over, minus, just kidding, minus 1 all over 3 over 5 minus 1. And since 3 over 5 is smaller than 1, this goes to 0 and you get whatever, finite, something finite. So this one converges, and then you can declare the original series converges by limit comparison test, comparing it to this one. Yippee-ki-yay. See that? An easy example, but it has all the right key steps. The smelling part, the verifying part, the checking the conditions, and the conclusion. Yippee-ki-yay. Alright, come back for another example. See you guys.